All right, welcome everybody. Today we are delighted. This is the second meeting of the Harvard's Sports Analytics Lab and the American Statistical Association section on statistics and sports seminar series for the fall. And we're delighted today to have Harry Spearing. Harry's a final year PhD student in statistics from the UK. After completing his undergraduate degree in physics at Lancaster University, which specialized in astrophysics and cosmology, Harry continued at Lancaster, where he joined the Story Center for Doctoral Training. His PhD, in collaboration with ATASS Sports, is supervised by Professor Jonathan Tawn of Lancaster University, and focuses on ranking systems and prediction in sport. The way that we'll be running today's meeting is if people have any clarifying questions throughout, please raise your virtual hand and we can call on you. But if you have any substantive questions, please save them for the end. We'll have a bunch of minutes at the end for Harry to respond to your questions. So without further ado, Harry, please take it away. So let's welcome Harry. Thank you.
Okay, thank you. Yeah, thanks Mark for inviting me. It's a real honour to be able to speak to you all. And thanks everyone for showing up. I hope you get something out of it, and yeah, I hope you enjoy it. So I'll just try and share my screen. Okay, can people see this? Excellent. Okay, so yeah, today I'm going to be talking about ranking and prediction in elite swimming. And yeah, this is joint work with my supervisors, John Thorne from Lancaster and Tim, David and Grace from ATASS Sports. So I'm going to start off with a really sort of simple question, which is, how would you compare the performances of two swimmers? Now, so on the face of it, it seems pretty obvious, right? We can just compare the two times and the fastest time is the best swimmer. But it suddenly gets a little bit more complicated when we try and compare swims between different events. I mean, say, how would you compare a men's 100-metre breaststroke time to a women's 200 freestyle time? And even more complicated when we try and compare between different eras. I mean, the same swim time in the same event from 50 years ago surely should be regarded as a better performance than the same times from today because of the advancements in technology and nutritional and training strategies and things like this. So this is kind of what we're after, is some sort of global ranking system. And FINA, which is the global body for sort of swimming, they have their own ranking system, which compares swimmers over all 34 of the 50-metre, so the long course events. Now their system is a points-based system. So if a swimmer I in event J swims time TIJ, they get the points, sort of PIJ here, which is, so where RJ is the world record, it's simply a measure of how close you are to the world record in your event. Now, I mean, apart from this being completely arbitrary, there's some other issues. I mean, it's very sensitive to changes in the world record. You know, you could imagine someone absolutely smashes the world record in your event and suddenly you drop down the global ranks. Similarly, you know, by the same token, there's sort of bias within events where some events are considered more, or some events have world records which are considered better than others. So a good ranking system should be robust to changes in the data. And also we'd like to quantify uncertainty in the ranks perhaps. But a good framework might also have other features of interest. We might be able to tell what the ultimate possible swim time is. You know, maybe there's a limit to how fast we can swim. What's the swim time of the next world record? When will the current records be broken? And indeed, in which event is that likely to be? And we might also be able to adjust for technological advances. So part one is we're going to be talking about individual maxima. So each swimmer only has one data point associated with them, which would be their fastest time in that event. And this is to do with the paper that we're looking at today. Now, this is what my data looks like for a given event. So this is the men's 100-metre butterfly. So you can see we've got the fastest 200 individual maxima. So each one of these points represents a different swimmer, and it represents their best swim time and when it was swum. And this is just a frequency, histogram frequency. So we can notice a few things straight away. I mean, the first one is there's a clear trend in the rates of occurrences. As we go over time, we're getting more and more observations. The second thing we notice is actually this swimsuit effect. So you can see there's a massive increase in the rate between 2008 and 2010, and you can also see it in the points here. And this was due to the swimsuits that were introduced sort of around 2008, and then some further suits came in 2009, and then they were subsequently banned by FINA at the end of 2010. So we'd like to model that, and you can't actually see this in the data, but actually what we found was that observations above a threshold have a time-independent distribution. So what that means is, I mean, there's a natural threshold introduced here because we can only look at times that are faster than the 200th fastest time in that event. So we're only interested in times above or below that, I suppose. But they have a time-independent distribution, which means that actually given, so if we take into account the number of swims, given a certain number of swims, they actually have the same distribution. So we want to model both the rate of these times and the distribution of them. So for example, in a given year, what sort of distribution are we getting for the swim times? So to do this, we need some theory. And yeah, we want to model both the rate and the distribution of these extreme events. And they are extreme because we only have sort of 200 of the best ones over a 20-year period. Now, yeah, by definition, because they're extreme, we've got very few observations. You know, we don't know what the general sort of population of swim times are, but even if we did, it wouldn't be very useful actually anyway. I mean, I'm sure I don't need to go through this, but just the toy example, I mean, say we had some data X given by this histogram, and this is sort of the population, so this could be the population of the body of the data, and actually these two models, the orange and the blue, when you look at AIC and other fit criteria, they fit both pretty well almost equally well to the data. But when we actually try and predict the most extreme point in the data, you can see there's almost an order of magnitude of 2 in the probability of observing this extreme point. So modeling the bulk of the data wouldn't help us model the tails anyway. And so a separate framework for analyzing these extreme events is what's required. And this is where extreme value theory comes in. So in general, there's 2 main ways that this is done. The first way is by block maxima. So if we go back to our sort of dummy data here, we could see that what we could do is actually break this data up into, for example, here we've done it by year, and actually just pick the maxima within each year, maximum value within each year. And what we find is if we do this, then as the number of observations increases, the distribution of these maxima is going to converge to the generalized extreme value distribution function. And okay, it is the only non-degenerate distribution for these maxima. The second way we can do this is by looking at peaks over threshold approach. So if we choose a threshold, and there's a lot of historical debate about how to actually do this, but if you choose a threshold and just look at the data above this threshold, then as the number of data points increases and therefore the threshold can increase, actually this converges in distribution to the generalized Pareto distribution function, which is shown here. And so there's kind of 2 different ways of modeling extremes, and the distributions look something like this. So this might be a yearly maxima, and this is conditional, we're above the threshold, what's the distribution of observing a certain value. Now, we obviously, we, like many distributions, we can control these, we can change the location or the scale, but actually the important one is this change in shape parameter, this psi. And the reason is because it can actually tell us something about the physical, the nature of the thing that we're trying to model. For example, a shape parameter that's positive means that there is no upper endpoint to the distribution. So we can get arbitrarily large values. So, for example, if you want to model something like wave heights, clearly we would expect a non-positive, a negative shape parameter, because there's only a certain height that waves can get to, right? So that's quite a nice feature. But actually, what we're going to be using is the point process framework, and this sort of combines the two. So we combines the annual maxima and the peaks over threshold methodologies. And if you're interested in this, this book, the Coles book, is really good actually for this. So we define a point process, a Poisson process, where we have our times scaled between 0 and 1, and our distribution and our observations with scaled by some norming constants. And if we do this, we actually find that the rate is governed by this equation, which kind of looks a bit horrible, but actually it comes from the generalized Pareto distribution function. Now, it connects these parameters. So if you remember, we had the location, scale, and shape from the GEV distribution, and we have a different, slightly different scale parameter and a shape parameter for the GPD distribution, and these are connected like this. Okay, where this is, remember, this is the threshold, this U. So yeah, we want to model both the rate and the distribution of this extreme data. And now, because we have this point process, our observations are going to, or Poisson process in this case, because they're independent, they're going to occur by a Poisson process, where the rate is determined by these parameters, which now we're observing that they could be a function of time as well. And the distribution of the swim times, given they're above this threshold, which remember is defined by the 200th fastest time. So anything faster than this 200th fastest swim time, the distribution of these is going to be governed by the peaks of a threshold or methodology, which is the generalized Pareto distribution defined by these parameters. Yeah, so now we have something that can model both the rate and the distribution of these points, which is what we're after.
And are you? I'm sorry to interrupt, Harry. So you're basically doing this on the bin data. So from year to year, you basically have like counts of the
yeah. This is a continuous process, yeah. So it's not binned at all. It's completely continuous. So this function here, which controls the rate, you can have any time here. Yeah. Well, yeah. So this was just a demonstration, really, but yeah, it is not binned. It's continuous. And yeah, we wanted to model these three things really, in particular, the trend, the swimsuit effect, and the fact that the observations we're finding actually have a time-dependent distribution, given they're above this threshold, or faster than this threshold. So the way we do that is by adding in 3 extra parameters. So for an event E, okay, we have remember we have 34 different events. We have a shape parameter, location and scale parameter, which are the standard extreme value parameters. And we also add in a beta parameter, which is going to control our trend. And we're going to have 2 of these, 2 other parameters, which are going to control the swimsuit effect. Now, the reason we have 2 is actually, we found that there was a significant difference between the swimsuits in 2008 and the swimsuits in 2009. And actually that was needed to be modeled. And so the way we introduce this is quite simple. We take the, so in a given event, we take the shape parameter to be constant, and this is something that is quite regularly done in a lot of extreme analysis, because the time dependency can often be modeled through these other 2 parameters. And here we're saying that there's simply a linear trend, or some sort of linear trend in this parameter, and that the shape parameters are occurring, the swimsuit parameters are occurring through indicator variables, where if the swim time occurred in 2008, we sort of change that a little bit. Now, the scale parameter is almost exactly the same in its formulation, but actually, if you can see, it's pre-multiplied here by this shape parameter. And the reason we do this is, if you remember the definition for the scale parameter for the GPD, which is given as this, actually when you work the maths through, it gives us a time independent scale parameter. And so both the scale parameter and the shape parameter are time independent. And so we get this property that we desired, which was that given we're faster than the threshold, we've got a time independent distribution. So it's quite a nice sort of formulation really. So that's 6 parameters for each event. And there's 34 swimming events. So that's 204 parameters in total, which seems quite a lot. And the idea is that the robustness and predictive power can be improved by pooling information across the events. So the first thing we did was to try introducing distance as a covariate. Now a log-log relationship works with distance works really well for athletics actually. If you look when you do sort of extreme value analysis, and you have your log distance on the x-axis and the log of the parameter values, it works really well. But as soon as you want to try and pool between the different genders, it doesn't work. Obviously, it can't work. And we want to do pool across genders and also strokes as well. So if you tried to do that, it would look like this. Now I'll explain what you're seeing here because there's a lot going on. So this is the log of the distance. So for example, that would be the log of 50 meter, 100, 200 meter event. And this would be against the log of the parameter estimate. So we split it into 2 to make it easy to see. So for example, this would be the scale parameter for the women's 800 meter. So it's color coded with these at the bottom. Okay, so you can clearly see if we use the log distance as a covariate, well, it's not going to work very well. You can see there's still lots of variance between the events, and moreover, it's going to be biased because, for example, the breaststroke tends to always be slower than the freestyle, and so the parameters will always reflect this. So there's no smooth, continuous sort of function we could use to go through these points. But what if we use the threshold time as covariate? So if you remember, each event has got 200 observations, and therefore it has its own different threshold given by the GPD distribution. If we then use the threshold time as covariate, then things change. Suddenly we've got this really nice, if not linear, then smooth sort of distribution of these parameters, which hopefully we can then pool together. Okay, so now we're trying to pool together these 34 different events into some sort of hierarchical model. Now, one way to do this would be simply to use linear models. So for example, this pink one here, we could say the log of the location parameter for an event is just a linear model. Linear with the with respect to the log of the threshold, which is defined here. And actually, this worked pretty well, apart from the scale parameters. Okay, so these, for some reason, didn't fit very well, and they're quite sensitive to small sort of changes, and so we needed a bit more flexibility really in the modeling. And so instead of a linear model for these scale parameters, we actually used some non-parametric techniques. So we use splines. So I'll quickly describe what splines are. We use B-splines. So B-splines are essentially just these basis functions, and we have lots of these. And actually what we can do is just change the height of these, so we can multiply them by something. And depending on what we multiply them by, we can essentially get sort of any function we really want from this by adding in extra splines or adding in different heights. And then of course you penalize this as well. And so this gives us lots of flexibility. And the equation looks like something like this. Okay, so we have our B-spline and we have our different weights that we multiply them by. And so we use a spline for the scale parameters, and our final model looks something like this. So it says the full model is therefore semi-parametric with linear relationships for the majority of these parameters, of the 6 different things we're trying to capture. But we have a spline which models the scale parameters, and it just gives us that little extra bit of flexibility. So actually in the end, we got down from 204 parameters to something like 15 degrees of freedom. That's sort of 15.3, I think it was, degrees after check. Yeah, it was so much better than before, really. So let's get back to the data. So we wanted to obviously model the rate and the distribution. So the rate, this is the fitted rate of occurrences. So we can see that it's fitting quite well. We've got the red crosses, which is the data, and we've got our model with 95% confidence intervals. And they're all within 95% confidence intervals mostly. And the nice thing is that we're even fitting well within these swimsuit years, which is good to see. So we also wanted to model the distribution of these times as well. And just by eye, it looks to fit pretty well. Of course, we did proper tests as well. But we have our data, and this is our GPD distribution. And so because we had a negative shape parameter, which is kind of good, it's what we expect, there is a cap on how fast human beings can swim. We have an ultimate possible time, which is predicted by the model, and our world record, and of course our threshold. So, I mean, first and foremost, this is a ranking system. And so we define rankings by the rate at which a swimmer's best time could be surpassed by a new swimmer. So it's the rate at which we're getting, so if delta t is, for example, so in this case, now we do have to sort of bin it a little bit. So delta t could be a year, for example. And so we have the number that we're going to be getting in a given year. And then given that we're above the threshold, what's the probability of beating this time? So that's our sort of rank, the way we define our ranking system. And we get a ranking that looks like this. So yeah, we can see sort of Adam Petey's here. So first place at the bottom here, up to 20th place, with the confidence intervals, which we got from sort of bootstrapped estimates.
Does this depend at all on X, or is it monotonic in X, so it doesn't matter?
What's that, sorry?
Does your ranking criteria depends on little x?
Yes. So if little x is the time swum, then it's the probability that we could come along and swim faster than that time, given the year that it was swum. Okay, so you're selecting X to be the value for the current year. Yeah, so for a particular swimmer. So yeah, so that would be their fastest. Because you could because in principle you could arbitrarily choose that to be anything. Just like having some gold standard value and then rank according to that. Yeah. Okay, I just want to check and make sure I understood. Yeah, I think yeah. Yeah. So yeah, so for example, Sarah Surstrom and Katie Ledecky, it's looking like, they are first and second always. That's not going to change given the data we have so far. But we have one thing that's good to see is there's a good mix of men's and women's events, good mix of distances, and a good mix of strokes as well. So it's looking like it seems to be quite fair, but obviously that's something that's a little bit more difficult to test. Yeah, we said at the start that a good ranking system actually might be able to have some other features of interest, and one of those is the expected swim time of the world record. So this is the expected next world record swim time, and it's normalised by the current world record. So these should all be below 1. And so, for example, we're seeing here that the 50-metre women's fly, the next world record, we're expecting to be sort of around, 99.5% or something of the current world record. And now these are the ultimate possible times, which is defined by the upper end point of that GPD distribution. And you can see for these so for these two times here, so Katie Ledecky and Sarah Surstrom, it's reckoning that they're actually so which correspond to this time and this one over there, so the 1500 meter women's free. It's looking like they're actually really quite close to the ultimate possible time. So we're seeing that the ultimate possible time is only 97% of the current world record, whereas these other times are a lot lower. So that sort of matches up quite nicely. As well as that, we were interested in the time until the next world record was broken. And again, you can see these two are way ahead of the others. And yeah, the probability of the next world record being a given event. So there's all these nice results that come out of the model. But the other thing that we were interested in is adjusting for technology. And so we can adjust for the swimsuit. And obviously it depends which swimsuit it was, if it was the 2008 or the 2009 swimsuit. But what this table shows is all the events whose current world record is was swum with a swimsuit. Okay, and actually we have our world record, so current world record, and then we have this adjusted world record, which is what the model thinks the world record would have been if they were not wearing a suit. And then we have the non-swimsuit world record, which is the next fastest time that was swum without a swimsuit. And the interesting thing is that only 2 of the current world records, according to the model, would still stand if no one had been wearing swimsuits at all, which is kind of, yeah, quite an interesting finding, I think. So that was the part 1, which was based on the paper. I'm quickly going to go on part 2, it's quite a bit shorter, but we've sort of been talking about, we're going to talk about the things that I'm looking at the moment, which is a longitudinal approach. So if you remember, I made this assumption that, so we sort of made an assumption that, yeah, each swimmer's fastest time could summarize their whole career, because we only had the fastest data point. And this is something that we need to look at and think, is this actually a good assumption to make? I mean, on the face of it, it seems like it probably is, because we're interested in ranking people throughout the eras, and therefore their fastest time is probably when they were at their peak, and therefore it doesn't necessarily matter what their other times were. But this might not always be the case. I mean, a swimmer's fastest time may not even be their best time in terms of ranking. I mean, you know, if you envisage someone that swam 0.01 seconds slower but 12 years ago, because we're adjusting the trend, their fastest time might not even be their best time in terms of ranking. And also in terms of world records being broken, really this probability is actually, in the previous model, is actually a lot lower than it should be. And this is because really when we say what's the probability of a world record being broken in that previous model, what we're saying is what's the probability of someone else coming along, a new swimmer that we haven't seen before, and breaking that world record. Because only one swimmer can the model only recognises one event, one observation for each swimmer. And so, for example, the probability of someone coming along and breaking PT's world record is a lot lower than Peter going out and swimming a personal best, for example. So if we want to predict, we need to properly consider the longitudinal approach. And we now have this data which provides each swimmers the whole history of these swimmers' times. So we have a new data set. There comes obviously issues, and one of them is that swimmers may have different strategies. Some may pick a few events each year and work towards those. Others may go for the shotgun approach and just enter lots of competitions. So that's something we need to be careful with. Another thing, which is probably easy to fix, but you know, swim meets aren't uniform all year round. So for example, in July and June, there's lots of events, and there's not so many in December and things like that. The heats are treated differently to finals, although we would need to treat them differently to finals. You know, the top swimmers don't go out and swim their fastest in the heats, whereas slower swimmers might go out and swim their fastest in the heats. And so actually, this is also another way that swimmers have different strategies, and this is something we need to correct for. And kind of the main one really is independence. Okay, so in the previous one, we assumed independence. So in a given event, every swim time is independent of each other. But that probably isn't going to be the case anymore. And just to illustrate that, if we see a very fast observation at a particular time, that is an indication that there's a very fast swimmer present in the database, which we could then conclude that there might be other fast observations nearby because they're swum by the same swimmer. And so there's clearly some sort of dependence going on, which we need to model. So the way we do this is with this hierarchical model. So we have T, which are the dates, and we have our X, which we want to be GeV distributed. So these are the swim times. And overall, we have a point process. So this is lots of longitudinal, so this is longitudinal data. So this is data with lots of swimmers, still within a single event, who each have swum lots of different times. And what we want to say is that conditional on a particular swimmer, I, so let's say they have this random variable SI associated with them, that then their times and the dates at which they swum follow a Poisson process. Okay, so we've got these different Poisson processes that are conditional on a particular swimmer, but then when we look at the overall process, that's the point process. And this is the idea. And now it would be really nice as well if conditional on a particular swimmer, that their observations also follow a GeV distribution with separate parameters. And what this would give is almost like a random effects, well, I suppose it's a random effects GeV model essentially. So it's an extreme value process that we can apply to longitudinal data, really. And actually, we can get this. So we need to run a hierarchical structure, conditionally independent GeV distributions for each swimmer. And we can do this if we condition on a positive stable variable. So it's a bit of a horrible distribution, but if we let S be positive, have a positive stable distribution, and this S can somehow controls the ability of the swimmer, then we find that their observations follow a extreme value distribution with parameters given by these results here. And so we get this closed form GeV distribution. And actually, in fact, this is the only distribution that this would work for. So by only conditioning on a positive stable variable, can we get this random effects GeV model. So it's just just a little bit of an example really. We've got this just some simulated data. So now we're looking at swim speed, just because it was a little bit easier for simulation. And all these points here are GeV distributed, and they follow a point process. But actually, if we condition on a particular swimmer, so we have a blue swimmer, a red and a yellow swimmer, their points also follow a GeV distribution with parameters that can be written down, conditional on the swimmer's ability. And this is kind of the thing that we're aiming for. But like the previous model, we might want to put some sort of trend in, so we could do that quite easily as well by putting that on the parameters. But now there's something more sort of interesting that we can capture.
Yeah, so Harry, before you go on, I'm sorry. So is the only thing that distinguishes the swimmers is the S?
Yeah,
so
absolutely, yeah.
Each individual swimmer has their own S parameter?
Yeah, that is true. Yeah, so each swimmer has their own S, their own positive stable variable, and this is what's
and that'll be estimated along the way.
Yes.
Okay.
So we're aiming to estimate these global GeVs parameters, so the mu, sigma, and the psi, and then we estimate each swimmer's positive stable variable as well. So yeah, as obviously if you get more swimmers, that can be difficult to estimate, and you might want to put a threshold and sort of say we're only considering swimmers that are swum at least 50 times or something like that, because it can get quite difficult to model or for inference really. And so yeah, so we could have a trend as well, and that's quite easy to put in. But now we're considering that each swimmer has more than one observation, we can also put in other things like the career trajectory. So we're now sort of realizing that each swimmer perhaps actually has a peak in their career, which is quite an obvious thing to want to model. So there's lots of things that are playing off against each other, and it makes the parameters quite hard to identify. Another question of sort of interest is actually, where is this person's peak? I mean, it looks like the peak's around here, but actually there's a trend going on as well. And actually what was simulated as being their peak was around this point in time here. So probably this time might be their best in terms of ranking if we're adjusting for era because of the adjustment. So yeah, there's lots of things to consider. But if we do this, it gives potential for a proper predictive Bayesian model for forecasting world records, because we're now sort of considering that each swimmer has multiple swims, and we're considering their career trajectories with this nice random effects model. And we think it's probably, I think it's the first proper attempt at extreme analysis of longitudinal data, which is quite exciting. But there are some challenges. So inference is really, really tricky, and we're finding it quite hard at the moment. I think partly because the positive stable variable is quite ugly to work with, and also there can be quite a few identifiability issues and things like that. So one thing we are considering is using the sequential Monte Carlo approach, but really, yeah, any sort of feedback or advice you might have on this would be really useful here. So that concludes the talk. There's the Coles reference here, which is really good intro to extremes, and then this is the reference for the paper. And if you're interested, there's a link to my website as well. Yeah.
Great. Let's give Harry a round of applause. Thank you very much. We are opening up for questions. So people, please raise your virtual hand, and I can call on you. Okay, Richard, you're raising your actual hand, so hopefully that's
I don't know where my virtual hand is.
Fair enough.
Okay.
Very good. Go ahead.
Okay, so Harry, that was very nice. I want to make a somewhat off-the-wall comment. This isn't very well formulated, but I don't know whether you're aware of this, but there's been a whole series of papers by Brian Rich and Ben Shaby about constructions of max stable processes, which is building on this conditioning on a stable distribution idea. Mm-hmm. And their work is focused on the spatial extremes problem, trying to, if you're interested in precipitation extremes and how they vary over space, that's the sort of problem they're concerned with. But the idea behind the construction is it would work if you're doing time dependence as well, which seems to be what you're looking at. So, like I said, this is an off-the-wall comment. I'm not trying to think about how your approach is directly related to theirs, but it might be worth, and certainly they've done quite a bit of work on efficient Monte Carlo methods and stuff like that. It might be worth looking into that.
Yeah, that'd be great, actually. Yeah, I'll have a look into that. Noted. Thanks so much.
Rick, did you have a question?
Yeah, Harry, great talk. Thanks very much. I have kind of this, what you might call an application question. Have you compared, you've got that wonderful list of rankings with, confidence bands around it and which ones are really there. Is there in swimming any sort of world ranking or media or fan polls where you could see if your model is picking out different, is your model ranking performances differently or really consistently? I teach a math and sports course where I do a lot with ranking, and I always try and encourage my students when they've modeled something to then compare it to world ranking. So I'm just curious about whether you're, I don't know a great deal about elite swimming, but would fans of the sport look at your model and say right on, or would they say, that one's I'm curious how well it matches up with the athlete experience.
Yeah, so I mean, I haven't looked at it in detail, but there is a global ranking for swimming already, which FINA do, and it's like this point system based approach, and there are probably a few results in my rankings that people would be a bit sort of maybe shocked by, but actually it's because we're trying to do something slightly different, because we are correcting for the era in which the swim was swum, and so what we're interested in, given the date it was swum, how good were they compared to their colleagues, whereas the rankings for FINA would misalign. So it might be, my ranking system might be closer when we look at more recent times, perhaps, but it might also, because we're getting more and more times, a higher frequency of times, it's actually going to devalue those because of
and if I could just ask one follow-up, is there, I know in track and field athletics, there's often like little surges in records around world championship years or Olympic years. Have you thought about that? I mean, you have time in your model in interesting ways anyway, but I wondered if there's any evidence of that.
Yeah, this is something that we needed to look at, but it's one of these things that's quite difficult, because it comes down to, again, the way swimmers there's different strategies. So some swimmers really will pick out the Olympic years, and other swimmers won't necessarily. And in the first paper we did, we were only looking at maxima, so we only had one observation per swimmer per event. So that's not really something, we didn't really have enough data to do that, but it's certainly something that in this longitudinal approach will be worth looking at, because we'll have, hopefully sort of 50 to 100 observations per swimmer. And so we might then be able to pick out, that sort of Olympic year sort of blip, yeah.
Thanks, that's great. Good talk.
So Mani, I think you're next.
Hi, I'm Monty McGee from Southern Methodist University in Dallas, Texas. And I had a question about you said that you determined a threshold, and then you mentioned literature on the threshold, but they didn't elaborate. So I was wondering if you might elaborate a little on that.
Yeah, absolutely. So yeah, it has been the focus of a lot of historical debate, this how to pick the threshold. And there are ways of doing it. So a very common way of doing it, which is quite quick, is that you raise the threshold until you see the parameters, so particularly the shape parameter, starting to become steady. So you'll see as you raise the threshold, the shape parameter could go all over the place. Mm-hmm. And then at some point it will start to become sort of constant or fixed, as you raise the threshold. And that's one sign that your threshold is high enough. But yeah, I mean, it's a classic bias variance trade-off. I mean, if your threshold's too high, you're going to have massive variance. If it's too low, you're not going to be sufficiently approximating the asymptotic distribution. But I mean, I think a good way to do it is by cross-validation. So if you've got enough data, you can do cross-validation where you have a training set and you pick a threshold based on that and see how well it predicts the rest of the data and that sort of thing. So, but yeah, there's quite a lot on it. But yeah, good question, thanks.
Okay, so where would one start if I were to start looking at that? You have a good idea where to start?
Is in terms of literature? Or,
yes, literature, yes.
I can think of one, but I can't remember the name. I could send it to you after if you're interested.
Sure.
I've got one in mind, but I can't remember who it's by.
Okay. No, that's fine. That's fine.
Okay. And if you guys need to connect, just shoot me an email. I can give Harry's contact information.
Okay.
Okay, great.
Nathan, you have a question?
Yeah. Thanks for your talk. One slide that really interested me was the one where there was different events along the x-axis, and then the expected value of the next world record time, normalized to the current world record being 1. But one thing that was really surprising to me was the confidence intervals on those expected, on the black dots. The confidence intervals seem really small to me. So is that saying that you can predict the next world record time with just really high accuracy, or am I misreading that, I guess?
Yeah, so these are confidence intervals of the mean, not prediction confidence. So this isn't the confidence intervals that on the prediction, it's on the mean.
Got it.
So yeah, it's how confident we are that the mean this is actually the correct expected time, not what the range of expected time of next times are going to be, essentially.
I see. That makes sense.
And this is the same for all of these confidence intervals. They are confidence intervals of the mean, and these are so large because they're so dependent on the shape parameter, which in extremes modeling is always quite a difficult thing, is to actually ascertain what the value of that shape parameter is with high confidence.
Interesting. Do you have any notion of just what the prediction interval, how much bigger the prediction intervals would be on the black dots, just out of curiosity?
They would be a lot bigger, yeah.
Okay.
Yeah. Yeah, well, obviously, I mean, one of the reasons is because, we only have one observation for each swimmer in this analysis. But I mean, I guess that's the nature of extremes, is that, we are trying to predict something that we've never seen before, something that's more extreme than anything that's happened. And so prediction intervals can be quite large for those.
Yeah, makes sense. Cool, thank you.
Cheers.
So I see no other questions. I had one follow-up question. So when you determine your rankings, you're conditioning on the parameter estimates, and I guess I was just wondering if you thought about incorporating the uncertainty of those estimates into the rankings and whether that might have some effect.
So we did. Okay, yeah. So we did. What do you call it? Is it this? I'll just get the slide up. Is it easier?
Yeah, it's the one that integrates over the rate.
Oh yeah. Okay.
Because you're fitting your model and then you're.
Yeah. So we did bootstrap. The confidence intervals are sort of bootstrapped intervals. So we did parametric bootstrapping.
Okay.
So yeah, we simulated data for each event, lots of data sets, and then refit for those, and then those parameter, and then took the confidence intervals of those parameters, and then used that. So it is being incorporated there in these fits here.
Got it. Okay. Yeah, that's great. Anybody else have any questions or comments?
Hey, I had one quick question. I couldn't find the hand raise button.
All right, no problem.
And thank you again for this talk. One thing I was curious about, and I believe this might fit in more of the longitudinal approach, is looking if there were any effects on which lane the swimmers were racing in. And looking at that over time, I was just reading that there may have been some reduction in the pools in terms of the waves coming off of the outer lanes over time. So I don't know if that's something that would, just throw a wrench in some of these trends and create more parameters, but curious if you've thought about that at all, if there's any additional research there.
Yeah, I mean, this is something, when we first started, all these things we have to consider. And I think lane, from talking to actual swimmers, this is something that plays a big role, but it's something that we chose not to model, just because, the number of parameters then just increases, and I guess you have to stop somewhere. But it is, as you say, with the longitudinal approach, maybe with the more data, then that's something that we can also add into the model. So yeah, thanks.
Yeah, totally.
Any other questions or comments? All right, well, let's thank the speaker once more.
Thank you.
And everyone be on the alert for having another another talk in 2 weeks. And so just be on the alert for that. And thank everybody for joining us today. Have a nice weekend.
Thanks, Mark.
Okay.
Yep.
Thanks, Harry. Thanks, Mark.